Jnanam Paramam Dhyayam. Knowledge is supreme.
Okay, so now let us come to Artinry's lemma. So this is Artinry's lemma. So it says A Noetherian, A is an ideal in A, M is finite A module, and N is a submodule of M, A submodule, and we take this filtration on M, which is the given by the powers of A, so that is A power N M. This we know this is adic on M, and we take the induced filtration, that is you take this A power N M and intersect with N. So I consider this filtration on the submodule, and I want to prove that this is adic. So then the filtration A N M intersection N in N is adic filtration of on N on the submodule. So proof. So what a filtration, to prove some filtration is adic, the lemma says that we have to check that the module, the graded module is finite over the corresponding graded ring. So what is the corresponding graded ring is precisely A prime is our ring direct sum A power N, M prime was this A power N M, and N prime is direct sum A power N M intersected with N. And we know that because this filtration A power N M is adic on M, this M prime is a finite A prime module, since A prime A power N M, this filtration is adic on M, and by lemma. So by lemma and note that this ring A prime ideal A is in the Noetherian ring A, so ideal A is finitely generated. So let us say it is generated by A1 to AR, and therefore we have a map from the polynomial ring A x1 to xr to A prime. Namely, if I have to give a map on a polynomial ring in so many variables with base ring A, then I just have to give values on the indeterminate. So let xi map to AI. This is also A algebra, this is also A algebra, and this map is clearly surjective. because A prime as a algebra or A generated by the first component, it is a standard graded A algebra. See, this is A direct sum A and so on. So, it is generated by the first degree 1 elements. So, anyway, this map is A algebra homomorphism which is surjective. Therefore, by Hilbert basis theorem, because this is Noetherian, the homomorphic image of a Noetherian ring is Noetherian. So, by Hilbert basis theorem, A x1 to xn is Noetherian, xr is Noetherian. And hence A prime is Noetherian. So, A prime is a Noetherian ring and M prime is a finite modulo over A prime. Therefore, M prime is finitely generated. So, M prime is a finite A prime module, and this N prime is a submodule of that. It is a finite module over a Noetherian ring. So, M prime is Noetherian. Therefore, N prime is finite A prime module, and that means by lemma the filtration A and M, induced filtration on N is adic. Okay, now let me deduce some corollaries from here. So, corollary 1, that is usually called Krull's intersection theorem. Okay, so A is Noetherian, A is an ideal in A, and M is a finite A module, and N is the intersection of all A and M, all the terms in this filtration, adic filtration, A power N M. Then A times N is equal to N. Proof. Look at N. I want to prove start with N. Obviously, if I take A power N M intersection with N, because N is the intersection of all of them, this is same. This is a bigger set than N. So, when you intersect, you get the same thing. But for large N, this filtration is adic, means this means it is A times A power N minus 1 M intersection N for large N. But again, this is N. So, this is same as A times N. That is what we wanted to prove. Is equal to N. Okay, corollary 2. Actually, this is called Krull's intersection theorem. This is also, some people call it Krull's intersection theorem. So, assumptions as in corollary 1, and also I will assume that This ideal A is contained in the Jacobson radical of A. This is standard notation for the Jacobson radical of A. Then intersection A power n m this is 0. This is immediate from corollary 1 because we know A times n is equal to n. We know n is submodule of a finite module over a Noetherian ring, so it is Noetherian, and Nakayama lemma with corollary 1 will tell then n is 0, that is precisely this is 0. So, let me just write. So, proof by corollary 1 A times n equal to n, and n is finitely generated, A contains Jacobson radical, so on. So, therefore, n is 0 by Nakayama lemma. Okay. So, next corollary, this is a special case of corollary 2, namely suppose we have an ideal A contained in MA, the Jacobson radical, and of course we are assuming A is Noetherian. Then intersection A power n this is 0. See, these corollaries are very important when one studies. You see, each filtration will give the topology on the ring A or metric even, and then we want to study this metric space. So, one completes the metric, and then you on the metric completion there is a ring structure, and then one studies this complete local ring. This is a complete ring, complete local ring, and the properties of this ring associated with the properties of A. It's an interesting study which will also give some analytic considerations. Okay. So, now let us get back to our lemma which we wanted to prove. So, the lemma we wanted to prove was we have an exact sequence. So, proof of the lemma I am writing. So, we had given an exact sequence of short exact sequence of A modules. A is local now, and M is the maximal ideal, and Q is M primary ideal. So, such exact sequence, and we have given the middle one is non-zero. So, first is also we may assume the M prime is non-zero, otherwise nothing to prove. If M prime is 0, then this will be isomorphic, and then they are the same polynomial, so the degree will definitely drop. So, we can assume M prime is also non-zero. Now, when you tensor the sequence with A power q n plus 1, then we get tensor product is not a left exact. So, we will only get from the right side. So, we will get an exact sequence like this: M prime divided by q n plus 1 M prime to M q n plus 1 M to M double prime to q n plus 1 M double prime to 0. This is exact. But to make it exact, I will intersect, I will go further modulo the, so to make it exact, I will have to intersect this with M prime. Yes, so we will get an exact sequence like this: 0, m prime intersection with m prime intersection q n plus 1 m to m q n plus 1 m to m double prime q n plus 1 m double prime to 0. When you compare the lengths now, I think we came to this equation also last time. We put this is equal to, we put m prime n to be equal to m prime intersected with q power nm. So from here we will get equation like this, pq, so again alternating, so pq m at n equal to pq m double prime plus fn, where fn I will put fn is length of m prime by m prime n plus 1, and that also has a finite length, because you see the support of this consists of only maximal ideal, therefore it will be finite length and so on. So if I put this, then q from here we will get equation like this, q equal to pq m prime plus pq m double prime minus pqm. This is what we are interested in, finding the degree of this, and this is equal to pq m prime minus f. And so we need to prove now that, so the claim is pq m prime and f have the same degree and same leading coefficients. Because if you prove they have the same degree and same leading coefficient, the degree will get cancelled and then the degree will drop. So once you prove the claim, the assertion will follow. So enough to prove the claim. Okay, so we have this, so just write down the definition. So that means we want to prove that pq m prime at n, this is the length of m prime divided by q power n plus 1 m prime, and fn is this length of m prime divided by m prime n plus 1. So now this is where I have to use Artin lemma. Artin-Ries lemma says, by Artin-Ries, this q times m prime n will be equal to m prime n plus 1 for large n. This is precisely the, so remember, yes, where I put m prime of n, m prime suffix n, remember where did we put, that was here, m prime n is this, the induced filtration, induced q-adic filtration on m prime. So, because of Artin-Ries, this is m-adic. So, that means this, and therefore, so this is this is true for all n bigger equal to some stage n0. So, therefore, if I take q power n times m prime suffix m, this is same as m prime m plus n. Just keep applying this. So, you get, so because of this, q power m, q power n times m prime, this contains q power n m prime m, which is equal to m prime m plus n, which contains q prime m plus n times m prime. This is for all n. So, the length, when I go mod this and compare the lengths, we will get length of m prime by q power n m prime. This will be less equal to length of q prime, length of m prime mod this. This is less equal to length of m prime by q power m plus n m prime. Actually, that m, this m is n naught, this is n naught, this is n naught, this is n naught, and this is n naught. So, this is n naught, this is n naught. So, therefore, this is nothing but this one is pq m prime evaluated at n. This is less equal to p, this is no, this is not p, this is f n plus n naught minus 1, and this one is pq m prime evaluated at n plus n naught minus 1. So, this is a polynomial in n, this is a polynomial, n naught is fixed, this is a polynomial in the translated polynomial. So, therefore, this is caught in between that. So, that proves the claim. So, this proves the claim, and hence the lemma. Okay, the next one we want to compare the degrees. So, the next one is, so the next lemma is, when we have an exact sequence, short exact sequence like this, and q is m primary, and remember our assumption that am is local, and all these are finite modules, and dm we have put dm, this is the degree of this polynomial pqm. It is a polynomial with rational coefficient, and the degree we are calling it dm. So, what we want to prove is, if you have a short exact sequence, this degree is the maximum of degrees which will come from m prime and which will come from m double prime. So, proof Remember, in the earlier lemma we have proved that if I take the degree of the alternating sums of the polynomials, so that is degree of PQM m prime plus PQ m double prime minus PQ m, this degree is strictly smaller than degree of PQM. This is what we proved in earlier lemma. By earlier lemma, so from this assertion is clear, because the degree will be the maximum of one of them, otherwise this will not get cancelled quotient. See the degree, if the degree is not maximum, so this leading term is getting cancelled from these one. So either one or both will contribute, in either case it is a maximum. Okay, so the next one is, next lemma says that this degree is, we have seen that the degree of PQM, this is bounded by minimal number of generators for Q, but so this lemma says that this degree is independent of Q. That means if I take a different m primary ideal and do the same, form the numerical function and take its a polynomial function corresponding to that, then the degree will not change. So the degree is invariant, and this degree we will connect it to the Krull dimension. That is what precisely what will be called a dimension theorem. Okay, so to check that this degree is independent of Q, enough to prove that this degree is same as degree of the degree corresponding to polynomial corresponding to the maximal ideal. So it doesn't depend on the ideal Q. Okay, so it's enough to show this, but Q is m primary. Take this is m primary and m is maximal ideal in an Noetherian ring. So that will imply that some power of the maximal ideal is contained in Q. So therefore, when I raise the powers, m power r n is contained in Q power n, is contained in m power n for all n. Now when I take the lengths, so length of m by m power r n m, this length, and length of m by q n m, and the length of m by m, these lengths, they are, because these are the smaller the ideal, bigger the length mod. So we have these inequalities. So that will mean that the polynomials corresponding to this for large n, the polynomials are Pm m, this is evaluated at Rn, this is bigger equal to Pq m evaluated at n, and this is Pm m evaluated at n. This is true for all n, not n minus 1. Or this is also minus 1. All these are minus 1, sorry. This is minus 1, this is minus 1, this is minus 1. Because our definition of PQM evaluated at n is m by m power q power n minus 1 m. So this, now see this and this is the same polynomial, So that implies the degrees are equal. See this. So from here it follows that the degree of the middle one PQM is same as degree of PMA. So that proves the lemma. Okay, so the next time I will do dimension theorem. That will in particular show that how does one compute the Crool dimension of a Noetherian local ring, and it is finite.